Around 1400 joules of energy from the sun hits every square meter of the earth every second. That's a lot of light. Light interacts with anything our eyes see, and so it's no surprise that there's a ton of information about the world around us stored in that light, even beyond just the obvious details like color. One of the ways we can use light to understand the world around us is through interferometry. Interferometric sensing, at its core, uses the wave nature of light and the behavior that occurs due to that wave nature to make measurements. More specifically, we exploit interference between light waves. What is interference? Let's take two light waves of the same wavelength. If both waves match up perfectly, they constructively interfere, meaning the amplitudes add up. These light waves are said to be in phase. If both waves are out of phase by 180 degrees, then they perfectly cancel each other out, producing destructive interference. The key idea here is, if both light waves are in phase at the start, how could they become out of phase at the end? Path length difference. In short, when two waves initially in phase rejoin at some later time, having traveled different path lengths, it's possible they may constructively or destructively interfere. To explain this idea, let's look at examples. In material science, we use interference in X-ray diffraction. Here, we have a nice model crystal. Let's say the space between the atoms is around the order of angstrom. To resolve this structure, we need light of comparable wavelength. Enter X-rays, perfect for this wavelength range. Now, let's look at how light interacts with the crystal. Suppose one ray hits the surface and bounces into the detector, and the other bounces off from the layer below the surface. We can see that the rays each travel a different amount, and by doing some fancy math, we can show that the path difference is shown by the famous Bragg equation for diffraction. This says that if this path difference occurs at a multiple of a full wavelength, then the two rays will still be in phase at the end. But if the rays incur a path difference that makes it perfectly out of phase with the other ray, we observe destructive interference. Hence, by varying the angle of incidence, we can extract information about the crystal structure of our sample. In medical fields, we use interferometry in tools such as phase contrast imaging. Suppose we take two light beams again, and one passes undisturbed into the detector, while the other passes through whatever specimen we place there. Due to the wave nature of light, the beam that passes through the specimen obtains a phase shift. Why? Because the specimen has a different index of refraction, and when light passes through the specimen, its velocity decreases and therefore the wavelength as well, while the frequency stays constant. Therefore, depending on what the specimen is made out of, the final difference in phase between the two beams produces constructive or destructive interference, and therefore it's a phenomenon we can image. While the physics might not be too simple, the benefits in biological research are immense. This kind of imaging is superior in many ways to traditional imaging, as it avoids the need to dye a specimen, which kills the cells. And remember, because we are simply looking at visible light for this application, we can simply image with the aid of a regular CCD or CMOS camera, unlike X-ray diffraction, which is a bit more complex due to X-rays. And finally, my favorite example. You may have heard of LIGO, Laser Interferometer Gravitational Wave Observatory, a massive interferometer that detects gravitational waves set off by the activities of massive objects in the universe. At its core, LIGO is a Michelson-type interferometer. It looks a bit like a plus sign, where two of the sides have mirrors at the end, and a beam splitter in the middle. A laser source sends a beam of light into the beam splitter, which then is sent off into both arms of the interferometer. Next, the beams each bounce off their respective mirrors and come back. Then they are rejoined and analyzed for interference. How does this detect gravitational waves? Well, the gravitational waves distort space itself. This means that as gravitational waves pass LIGO, one arm gets shorter and other gets longer. When this happens, the interference detected changes, since the path length has changed too. This whole arm shrinking expanding business actually oscillates back and forth until the gravitational waves have passed. And by looking at the change in interference over time, we can obtain information about the event. LIGO is not a simple interferometer, of course. The spatial stretching and shrinking is less than the size of a proton. Hence, there are key modifications to the design to increase sensitivity and resolution. For example, each arm is 4 kilometers long, but there are mirror cavities set up on each arm to cause the light to bounce 400 times in each arm before being rejoined. This causes the interferometer to have an effective arm length of 1600 kilometers each, which amplifies the change in interference behavior seen, since now the light is not just experiencing the gravitational waves once, but rather many more times. Interferometric sensing helps us understand the world around us, as well as characteristics of materials we can find and make on Earth. Furthermore, interferometry helps us probe the grander nature of the universe and aid us in our search for answers to the deepest questions in physics and beyond.